The recording is on now. Perfect. So, welcome everyone to CE305 Languages and Compiler, or as I also like to call it, the module on how to build your own compiler. Today, we will be going through like some of the most important concept of compiler and language design, that's grammar and parsing. We will be covering portion of it today. And as usual, we also have Amirul with us, your teaching assistant, who will be helping me with the Q&A section. So if you have any question, please put that in the Q&A of the lecture, and we will answer that as we progress through the lecture itself. So first off, grammar. A little recap on what we have already learned. So while looking into tokenization that we have learned in the previous lecture, we have seen the use of formal languages, automata, expressivity versus efficiency, and also implementability of the language. All of these foundational issues are in computer science. For tokenization, we only needed regular grammars. But for parsing, we will need something with greater power. Now, before we move on, who can say what is, let's say, if I ask you simply, what is finite automata? What would you say? A simple definition of finite automata. I've mentioned this last week. Let's say, put that in the chat, please. Anyone? Curtis, Matthew, Stefan, could you write? Okay, Matthew mentioned, sorry, got distracted, opening a jar for, okay. So Matthew, the question is, what is the simple definition of finite automata or automaton? What it is? So Dragos has mentioned a state machine that has a starting state, a grammar, and a finish state. Well, you are correct about having starting state and finish state, and then it has transition. So it is correct, like the features of finite automata consist of states and transition. But what does finite automata represent? Can someone mention that? Having a specific number of states without epsilons? No, it can have epsilons. If it has epsilons, then that's a non-deterministic finite state, like automaton. But if it doesn't have epsilon states and no multiple transition, then it's a deterministic finite automaton. So Curtis has mentioned, sorry, I was struggling to use keyboard. I think it has finite number of states and can be deterministic, non-deterministic. Yes, that is correct. Dragos has mentioned each input generates at most one state. Well, yes. Yes and no. That's true for deterministic finite automata, like transition, like will be unique from one state to the other. It won't have multiple transition for the same input. So you guys are correct in a way that finite automata, whether it's deterministic or non-deterministic, it has states and it has transition. But the core concept that why we have finite automaton, automaton is a singular form Automaton's other meaning or other word is machine. So it's a finite machine. So I have already mentioned finite automaton is technically an abstract computer. So it's a representation of an abstract computing machine. And in the computer machine, right, we change state from one to another based on the transition. And the transition happens based on the input. Now, keep this in mind, because from the finite automaton, we have already understood from the previous lecture that it is very limited. Because it's an abstract form of the computer, we do not have a lot of features that a modern computer do have, such as, let's say, memory. So is it clear now what is finite automaton or finite automata? Thank you, Curtis. Okay, moving on. So before we move on, at the end, as I have already mentioned, for parsing, we will need some form of computation with greater power. Rather than in tokenization, we can just use finite automata to determine what is a token from the input string. So keep this in mind. We have another person mention something in chat. Okay, thank you, Matthew. So in languages and automata, different constraints can be applied to the nature of the rules of a grammar. These constraints may restrict both the languages that can be recognized and also the power of the computational device required to parse using the grammar. Now, regular languages can be implemented using finite state system or finite state automata. Keep in mind that not all useful languages can be expressed using regular grammars. Finite state system and the rules of regular grammar have no memory, as we have already noticed, because it has states and transition. So in that case, they cannot count the number of times a particular symbol has appeared or a state that has been entered into. That's why we need more powerful computing machines or concepts that is capable of achieving that. Now, let's look into a problem. So if you have an input which is denoted by this, let's say within brackets you have 8 cross 2 plus again within bracket 2 plus 3 multiplied by 2 then divided by 10. As you can see, in order to specify the precedence, we have lot of left bracket and right bracket, or opening bracket and closing bracket here as part of the input string, which is denoted by here. So in this case, for the parenthesis to match, the rules of the grammar need to be able to express the requirement that by the end of the expression, the number of left bracket is equal to the number of right bracket. And at any point within the expression, we never encounter more right bracket than the number of left bracket. If we go, if we traverse it from left to right. So in this case, we have to make sure the number of brackets are balanced. We can't have one more than the other. So in effect, to parse a grammar that is sufficiently expressive to have matching parentheses, we need some form of storage. In general, to parse such grammars, we would need a stack in addition to finite state automata. A finite state machine can simulate constrained parenthesis matching, but the solution is not general and is not also easy to express or efficient to implementation. So is there any question so far? No? Good. Okay. Matthew asked, what do you mean by not general? Oh, give me 1 second. So what I mean by not general, it's because if a finite state machine is there, you can only traverse because you can change the state based on the input, right? And here the input could be even the parenthesis. So when we change state, we just are changing the state based on the transition. But there is no particular way of understanding whether the parentheses in this input are balanced or not. Let's say if I took out one of the parentheses from here and just use a finite state machine to traverse this and generate the token, then we will get the token, but we won't be able to tell that the parentheses are balanced. So in this case, like we are not getting the full picture of the relationship of each of the token that can have with each other. And relationship in the means, let's say here, if we have this within parentheses 2 plus 3, within parentheses, which means that 2 plus 3 needs to be performed here together. That's the whole point of having the like brackets, right, around them. So that kind of forms the relationship between how 2 plus 3 will be represented, especially in the parse tree format. But in finite state, we do not have any way of determining those. We just change state based on the transition, and that's it. So does that make sense? Matthew? Great. Thank you so much for confirming, Matthew. Okay, so in formal language theory, grammar defines how to form strings from a language's alphabet that are valid according to the language's syntax. So technically, grammar is the set of rules that will define if your input is correctly matching the language for which the grammar is for. Mathematically, we can express a grammar in the form of a tuple like this. And the tuple consists of n, t, p, and s. Here, n is a finite set of non-terminals. T is a finite set of terminals. P is a finite set of production rules in the form where alpha derives beta. So when we have this arrow sign, we can either say it produces or it derives. So this is one of the notation that how we can express production rules. So the way you said it is alpha arrow or produces or derives beta. And S, which is, it belongs to the set of non-terminals N, which is the start symbol. Now we have someone post something in the chat. Dragos has mentioned, can we say determines? Usually, so when it comes to grammar, we do not really say determines because this is grammar consists of production rules. Remember, we have already gone through that in labs and in lectures as well. So if something is a production rule, so technically it should be like something produces something or something derives something. It's a better terminology or language to use that. Now, a very important kind of classification system that is used in context of grammar is Chomsky's hierarchy. The Chomsky's hierarchy is a containment hierarchy of classes of formal grammars. It is technically a characterization of languages where the corresponding grammars are classified according to the kind of rules permitted, the kind of sentence structures that can or cannot be recognized, and based on the kinds of automata that can implement parsers for that particular class of languages. So this is on the right-hand side here. This is a diagrammatic representation of Chomsky's hierarchy. So Chomsky's hierarchy has 4 different types of grammars, and the class of language it generates depending on the 4 different types. So we have type 0, which is the unrestricted grammar. We have type 1, which is context sensitive grammar. We have type 2, which is context free grammar, and type 3, which is regular grammar. Now we will be going through each of these type of grammar very shortly, so please bear with me. Okay, first off is regular grammar. A regular grammar is a formal grammar that is right regular or left irregular. So that depends on how you're traversing or how you're parsing. Every regular grammar describes a regular language itself. So it is type 3 in the Chomsky's hierarchy, where how you determine it. So the rule is that A produces X or A derives X, B, and A derives X. So here, X itself is a terminal category. The computational power needed for type 3 grammar is, or type 3 grammar in Chomsky's hierarchy is finite state automata. And its characterized string will look something like A star, B star. So this is an example of the characteristic string for regular grammar itself. Now, the type 2 that we have in Chomsky's hierarchy is context-free grammar, which is, or we also call it CFG in short. So CFG is a formal grammar whose production rules are of the form A produces or derives alpha, with A being a single non-terminal symbol, and alpha is a string of terminals and or non-terminals where alpha can also be empty as well. So formal grammar itself is context-free if its production rules can be applied regardless of the context of a non-terminal. So you need to keep this in mind. Again, this is the type 2 in the Chomsky's hierarchy, and the rule is, it can be denoted like this, where A derives B, C, D, and so on. The computational power needed for this type of grammar is push down stack automata. And the characteristic string can be something like A to the power n, B to the power n, which is more like nested dependencies. So like nested loops itself. Here, another thing is that like what we are using this rule. So it's a left-hand side symbol is a non-terminal. So in this rule, the left-hand side symbols will be a non-terminal. You need to keep this in mind as well. Okay, we have someone post something in the chat. Dragus has mentioned, what is a push down stack automata? Did we cover this? We have not covered this. So it's a type of state machine where you have to, okay, I'm just thinking of how to mention this. So push down is a mechanism where, so Matthew has asked, does it uses states on the stack? Yes, it does. So it's more like it has a stack. In the stack, you have each of the transition. We stored the transition. So based on the transition, we do a push down method on the stack and we traverse it, if that makes sense. Right now, I might not have a good example with me, but later I can show you with a better example what is a push down stack automata. In the books also it is mentioned, so you can do your own research to find it. But at a later stage, I will bring a better example to show you what is a push down stack automata. So let me close the chat window. Moving on with context sensitive grammars. Now, this is the type 1 in Chomsky's hierarchy. So a context sensitive grammar, or also called CSG in short, is a formal grammar in which the left-hand side and the right-hand side of any production rule may be surrounded by a context of terminal or non-terminal symbols. Context-free grammar are more general than context-free grammar. Sorry, context-sensitive grammar are more general than context-free grammar, in the sense that there are languages that can be described by context-sensitive grammar, but they can't be described by context-free grammar. Especially if you can recall here, the rule, right, for context-sensitive grammar, that the production rule can be surrounded by a context of terminal and non-terminal symbols. So it can be both. Whereas in context-free grammar, what we have noticed that the left-hand side symbol of the production rule is always a non-terminal. But in context sensitive, it can be either terminal or non-terminal. Now, it can be denoted, like production rule for this type of grammar can be denoted as ABC produces ADC. Now, someone has posted something in chat. Are there any industry example of a context sensitive grammar languages? At the moment, Matthew, no, because although keep in mind that when we are understanding the Chomsky's hierarchy and the different type of grammar, these are, let's say, when the theories came along, that's like almost 40 years ago, there's 40 to 50 years ago, when the theory was being formed behind the languages and grammar. So these, what we are understanding or what we are learning now are more on the theoretical side. In modern world, most of the languages, they fall in terms of context-free grammar, which we will be discussing shortly. But although most of the modern programming languages follow like context-free grammar, the issue is oftentimes many languages can also be inspired or use some concept from other form of grammar as well. So it's more on the hybrid side, especially because modern languages are far more complicated and they are not pure in its own sense. But again, most of the time, modern languages still follow context-free grammar side of the grammar itself. Dragos has mentioned, so I think Chomsky is talking about human languages rather than computer languages. Chomsky's, yes, but it's not just about human languages. Chomsky's hierarchy can also represent computer languages as well. So when we say languages, we mention languages in terms of linguistics, which is not just, let's say, human form grammar or languages, but it can be any form of language. So linguistics itself is a completely separate, let's say, field of study. And linguistic just doesn't consist of human languages, but it can also have languages in different form, like other animals as well. They can use sound, right? Sound is also a form of language, of communication. But how it's represented, that varies. So yes, Dragos, you are partially correct that Chomsky's hierarchy is initially kind of meant mostly for human languages, but it can be used for more as well, as I've already mentioned. Now, characteristic string for context-sensitive grammar could be something like a to the power n, b to the power n, c to the power n, and so on. It's more like to show the cross-serial dependencies. And keep in mind that the number of left-hand side symbol is less than equal to the number of right-hand side symbols in context-sensitive grammar. Now, the type 0 of Chomsky's hierarchy is the recursive enumerable grammar, or we also can call it the Turing. So recursive enumerable grammar, or Turing, acceptable languages will enumerate all valid strings of the language itself. Recursive enumerable languages are also known as type 0 languages in the Chomsky's hierarchy of formal languages. All regular, context-free, context-sensitive, and recursive languages are actually themselves recursive enumerable. So, excuse me, the production rule for recursive enumerable grammar looks something like this. Anything can produce anything, or anything can derive anything. That's the whole meaning. And one representation of the automata for this type of grammar could be general Turing machine. So I'm sure you must have heard of Turing machine by now. So that is a form of like finite automata representation of recursive enumerable grammar. And the characteristic string here is that any dependency is absolutely completely acceptable. Excuse me. So increasingly more powerful automata can parse increasingly complex grammar families from type 3 to type 0 of the Chomsky's hierarchy. Unfortunately, more powerful formalisms have some unpleasant properties that are related to the halting problem. So the halting problem is a problem of determining from a description of an arbitrary computer program and an input whether the program will finish running or it will continue to run forever. That's the halting problem. So fortunately, programming languages and most human languages are expressible in context-free grammar. So as I've already mentioned earlier, programming languages in general require something less than the full potential of context-free grammar, while human languages are sometimes, they require slightly more expressiveness than context-free grammar itself. Even so, computational complexity of parsing may be high, and some obvious questions are undecidable in this case, which is the equivalence relationship that we have also covered in during the finite state automata. Now, Chomsky's hierarchy is not just the only classification that is out there. There are other different forms as well. But Chomsky's hierarchy, we study it because it's a pertinent one for theoretical computer science. When it comes to programming languages, other relevant classes also include LLK, and LRK. So we will also explore some of these at a later stage, which is like right derivative or left derivative, like how you are parsing the input itself. So based on right to left or left to right, that would be determined. And we will call this, if you see LLK or LRK, these are here, the K is the number of look aheads that will be used. So we will, if you do not understand these ones right now, do not worry, because at later lectures, we will be exploring these topics as well. Now, when it comes to linguistics, there are other relevant classes, include like weakly context sensitive grammar as well. Okay, now remember, as I've mentioned, programming languages almost always fall within the context-free grammar. So let's understand a bit more about this topic. So if we have regular grammar, which let's say is denoted by G, and G equals the tuple, which is N, T, P, and S. If we assume this as a regular grammar, then all the productions are in the form where capital A produces or derives small a, where capital A can be the non-terminals and small a can be the terminals. Or you can also have the production rule, which is capital A produces or derives small a capital B, where capital A and B are the non-terminals and the small a are the terminals. So this is the production rule that context-free grammar generally kind of will be following. Another thing, you can also have epsilon productions as well, which is of the form that capital A produces or derives epsilon. This means that A does not appear as a substring on the right-hand side of any other production in P. So here, based on the grammar that we just noticed, G is a context-free grammar if the production rule in P are in the form like this, where capital A produces or derives alpha, eta, and beta, where capital A are non-terminals, alpha and beta are can be non-terminal or terminals, and eta can be non-terminal and terminal to the power plus, which means it recurs to itself, if you can recall from the previous lectures. So the recursive syntactic structure of programs can be defined by context-free grammar. Few characteristics of CFGs is that CFGs have terminal symbols denoted by T. You have non-terminal symbols denoted by N, capital N. You have start symbol, which is like it distinguishes a non-terminal corresponding to the category of the largest structure that we wish to find from it. And then you have rules of the form, which can be denoted by X derives y1, y2 to yn, where X is non-terminal and Yj or Y1, Y2 to Yn, they can be non-terminal or terminal. Now, these rules tell us which categories we need and the order in which they occur for us to have the category X itself. So that's the production rule for context-free grammar. So the application of context-free grammar rules can be seen to generate the tree structure. Now, let's take example of this. If you have arithmetic expression, which we have already done in practical lab sessions as well. So you can have production rule where you can have E derives var id, E derives num val, E derives E plus E, E derives E star E. It can also derive minus E, or it can derive itself E. So these are the production rule or the total grammar for arithmetic expression. This is another example, but this one is the production rules or grammar definition for the Boolean expression, which is like self-explanatory on its own. Now, this example is the production rules or grammar for statements itself. Again, this is very self-explanatory on its own, and you can go through it on the lecture slide at your own time. Now, the next important thing that we should learn, and this is very important because we use this to represent the grammar or the production rules in a more simplified format, which is called the Backus-Naur form. So Backus-Naur form or Backus normal form is a metasyntax notation for context-free grammars, often used to describe the syntax of the programming languages. Alternative presentations of rules are, so how they're specified or defined is that it essentially uses an assignment sign, which is like a colon equal, or you can just assign using an equal in the place of the arrow. So if, let's take this example, right? Earlier, you have seen when we, in form of context-free grammar, when we were defining how to write the production rules or the define the grammar for context-free grammar, you notice that we showed here. So we are using arrow, right? But here we replace the arrow with an assignment sign, which is more like a colon and equal. And then we write all the forms like a production rule of the same non-terminal, let's say E here, using the pipe sign. So let's recap a bit here. As you can see, so the context-free grammar representation for arithmetic expression is written like this. So is the non-terminal where you have production rule like this, and you can see you have several production rules, right? The way to convert this to Backus-Naur form is you write the non-terminal itself, replace the arrow with colon equal, and all the production rules go by the side of each other using pipe sign, which will look something like this, as you can see. So it is that simple to convert context-free grammar into Backus-Naur form. And another thing from here to notice that Backus-Naur form or BNF, it's a compact representation of the grammar and can be written without using special symbols as well. We also have extended Backus-Naur form where you can use different symbols for other different options in the production rule. So this extended Backus-Naur form is an extension of the like Backus-Naur form itself by Nicholas Worth, and a version of it is also ISO standardized. So the standard for that is the ISO EEC 14977. And it defines that if you have a definition, it can be denoted by equal. If you have concatenation, it can be denoted by comma and so on. So if you access this ISO standard, then you will get all the like representation variation of the extended Backus-Naur form there. Now, let's take another example. Okay, before we move on, we have someone post something in the chat. Okay, Dragus has asked, is the alteration sign in eBNF different from the pipe used in BNF? What do you mean by that? So you are asking whether this alteration sign is different from the pipe used in BNF? If that is your question, no, it's actually the same. So alteration means it can be either or, right? The reason we call it extended Backus-Naur form, because Backus-Naur form, when it came out, it was very simple. It only had the definition and the alteration. It didn't have other forms such as, let's say, concatenation, termination, and grouping, and so on. So extended Backus-Naur form also considered those in terms of grammar as well. That's why it's called extended. So you will find more symbols that can be used to represent a grammar in eBNF form. But technically, there's not much differences between eBNF and BNF, because technically eBNF is an extended version of the BNF. Okay, so moving on. Okay, Soren has asked, why do grouping and comment have the same symbol? So it depends on, actually the representation is kind of different. So when you say grouping, here the ... means something goes in between, like the production rule, one of the production rule like will be going here. And if you put more production rule within the bracket, then that's grouping. Whereas comment, it's actually how you write command using the form in like eBNF or extended Backus-Naur form. So if you download the standard for ISO EEC 14977, it will make it far more clear that how to represent them. It's just that here, when we represent it here, this is more like just to give you an idea how to write it. So do not take this by heart. The full form of like how each and every symbol of like production rule can be expressed using eBNF, it's better to download the standard and you will be able to see them there. Got it, Saran? Okay, wait. I can only find it for purchase online. You do not have to do purchase online. The way to download these ISO standard could be if you go to IEEEexplore.com. So IEEE Explore is the digital library of IEEE. And there you will also find the standard as well. You can log in using your university. email. So because University of Essex is a partner of IEEE Explore, you can also log in through that digital library of IEEE, and you can also download the ISO version for free. Okay. And also, if you just Google for, let's say, the standard ISO IC and the standard number and then PDF download, then you will be able to get it as well. Yes, Dragos. So the one that you have shared, this is directly from the ISO. But because ISO partners with other like standardization companies such as IEC, IEEE, you will also get the same version from other places. Some of it which could be free, especially because IEEE has partnership with our university. Okay, so as we have already seen, so remember earlier we saw examples of different like arithmetic expression, Boolean, statement. Let's say if all of those production rules or grammar form one big language, then all the production rule can be represented using BNF form in this way, where this one is how E can be defined, like derived using the different production rules. Same for B, which is the Boolean, S for the statements. So BNF is technically, we just replace the arrow, and all the production rule are because they are alteration, we provide them using the pipe sign. And again, like you have the variation on eBNF, that is like not all sources use the standard BNF or eBNF notation. You have to keep that in mind. One example is the notation that defines the category itself. So common symbol that are usually used are like colon, equal, or equal, and arrow sign. But there can be slight variations in these as well in other forms. But because we are learning the theory behind this, try to understand and learn BNF and eBNF, which is far more important for you and especially for your exams as well. Now, next off is the other important part, which is the parsing. So remember last week we understood finite state automata and lexical analysis, but the next part is parsing, or which is done by the parser, which you should already know depending on the labs and the previous lecture. But before we move on to the parsing lecture, let's take a 5-minute break and we will continue after that. But before that, we have, oh, Curtis, good timing for calling a break. Yeah, so let's take 5-minute break and we will continue with parsing. Let me pause the recording. Perfect. Okay, is everyone back yet? Thank you, Curtis. Okay, before we move on, I have mentioned about parsing several times already. Okay, before parsing, what happens in a compiler? Can someone mention in the chat? Yes, tokenizing or tokenization happens. What is the output of tokenization, Dragos? No, Curtis. So I asked, what is the output of tokenization? A tree of tokens and operators. Technically, Dragos, you're correct. It doesn't form a tree. In tokenization, the output is tokens, and tokens can be symbols like operators, or it can be any of the alphabets like alphanumeric value. So the point of tokenization is that the output is the token, and token can be like streams of token, and token can be like symbols like operators and alphanumeric value that forms the whole string, input string. Okay, so remember that. But now the tokens will be used in the parsing stage. So moving on with the parsing itself. Excuse me. So parsing, or also called syntax analysis or syntactic analysis as well, is the process of analyzing a string of symbols or tokens in programming languages. Now, someone mentioned something in the chat. Matthew mentioned, or a stream of the words of the language with some information about them. That is correct. So when you have the stream of the words, technically it's the stream of the tokens. So words are the tokens. So for a compiler, we need a parser that has input and it produces the output. The input is the input lexems or tokens from the tokenizer, and it produces the output, which is the parse tree of the program. That's what parsing does. In practice, the parser may not actually produce the parse tree itself as output, but instead some other information that was generated in the process corresponding to the construction of the parse tree, such as abstract syntax tree or semantic interpretation. So those can also be output as well. So let's take an example. If you have the input, which is a equals 5 plus a, right? So the first process of the compiler that happens is tokenization, right? So you get the tokens, which is for this input, it will be IDA, assignment sign, ID5, add symbol, and IDA again. So these are the tokens generated from this input string. And then in parsing, you will get a parse tree or concrete syntax tree, which will look something like this. So this is the output that the parsing will generate if your input is this one. So let's look into the comparison between tokenization and parsing. So tokenizer takes a string of character and produces a string of tokens, whereas parser takes a string of tokens and produces a parse tree. Tokenizer's role is to recognize and assign valid tokens, whereas the parser may give helpful information in the event a program is valid or not, and at the same time, it also recognizes the valid program and allow a meaning to be assigned. For tokenizer, we have a language that state the rules about the valid tokens and the ways of using those rules to recognize the valid tokens itself, and also assign appropriate values where relevant. Whereas in the parser, we need a language for stating the rules about valid programs and an algorithm that uses those rules to recognize valid programs and assign an appropriate structure to it. Both tokenizer and parser may give helpful information in the event a string or program is not valid as well. So you can also understand errors from both tokenizers and parsers, but for different things. For tokenizer, you will be able to understand whether something is a valid token or not. Whereas in the parse tree, you will be able to understand furthermore, because you get the output of the parser is the parse tree, where you get more information about the hierarchical relationship between the tokens. So let's say you have the rule something like this, where X derives Y1, Y2 to Yn. Think of this as the rule or the instruction for this grammar. So if we have X, it can be replaced by Y1, Y2 till Yn. If we replace the X by Y1, Y2, Yn, that is called the top-down approach. Whereas if based on this, again, the same rule, if you replace the like Y1, Y2, Yn by X, then that one is called bottom-up approach. So you can apply the rules top-down, especially. The algorithm for that is that begin with the start symbol, which is the X here. So begin with the start symbol and then replace any non-terminal X by the right side of the rule to form X derives Y1, Y2 till Yn, and you continue until there are no non-terminals left. So that's how you approach top-down. So let's say you have, okay, someone posted something in the chat. Curtis asked, in other words, the way in which it expands until root or leaf. Yes, correct. So you have a top-down approach. So it can be thought at expansion, because you're starting from the left-hand side, which is the start symbol, which is X, and then you're expanding it based on the rule, which is, let's say, Y1, Y2 till Yn, so on. So Curtis, you are correct. Okay, so moving on. So let's say you have X1, X2 till Xi, Xn. We can actually obtain, so based on the rule that we have already noticed here, right? So you have the rule X derives Y1, Y2 till Yn and so on, right? Based on this rule, if you have X1, X2 and so on, then you can replace the X symbols, which are the non-terminals, with the Y1, Y2, Ym and so on. So we can write that, again, as we have already mentioned, if you have X1, X2 till Xn, we can denote that as long arrow followed by star Y1, Y2 dot dot till Ym. So this is a representation to say that the latter, which is this one, Y1, Y2 to Ym, can be derived from the former, which is X1, X2, Xn, in 0 or more steps. So whenever you see like a production rule having a long arrow and a star, it means the later part of the production rule can be derived from the former part in 0 or more steps. So let's assume we have a context-free grammar G, and the language for the grammar represented as LG. So generated by the grammar G will be all possible sequences of the terminals A1 to AN, which can be derived from the start symbol S using the rules that we have just explored. And the mathematical representation of such a language will be like this, where LG equals A1 till AN, And the S derives or produces A1 till AN, where you already remember long arrow and star determines that the A1 to AN can be derived from S in 0 or more steps. So that's how mathematically you can represent language depending on the grammar. We have Matthew post something in the chat. Is that just saying if you start from the start symbol and follow the rules, you will have a piece written in this language? Yes, not a piece written, but this one. So is the mathematical representation to say that if your start symbol is the S and you start from there, then you should be able to derive A1 till AN, whichever, like whatever rule is provided there. Okay. So this form is just the mathematical representation of a language following like context-free grammar. Does that make sense, Matthew? Okay, I didn't get any reply back, so I am okay. Matthew mentioned yes, although I'm not sure why it's need to be written mathematically. Okay, the reason why we need it to be like written mathematically. So for practical reasons, you do not have to be kind of worried about these things, right? Anyway, you have an antler which does most of the heavy lifting. In the like background process of antler, it already does all of this. But the one of the main reason why we understand the theory behind each of these, let's say some of you, after you graduate, you might want to go into academia for further study, especially in the research direction, right? In research, we want to define everything using metrics and formula. Or else if you do not understand or able to represent a concept in mathematical formula, it is often difficult to expand or improve on that. And again, also you are already aware that computer science is an applicative field of mathematics itself. Computer science evolved in that way. So most of the concept in computer science can be represented using mathematics. So what the reason why we are understanding, okay, why we need the mathematical formula for a language is because we are just defining it in terms of mathematics. Again, in practical senses, right now in the industry, you might not have to understand this as much. But let's say, again, if you start working at Facebook, right? Facebook currently is pushing towards metaverse. And I'm very sure in next 5 to 10 years, Facebook is going to launch several other languages from their research team, right? If you end up becoming one of the researchers at Facebook or even Google or other big companies who are doing research in languages, you should be able to know that how languages can be determined in terms of mathematics. Because if you also download some of the papers on this topic, you will see most of the researcher uses mathematical formula or representation to define something. So this is just for mostly for your understanding and also get to know how you can represent languages in mathematics. Does that make sense, Curtis and Matthew? Again, not everything that we learn throughout computer science is about just practical. Because right now, today, you might be going into industry for work. Later, you might want to like change field in a way that you don't want to work as a software engineer and you want to become a researcher. Then if you do not know the theory and mathematical, let's say, representation of important concepts in computer science, it might make it difficult for you. So this module, I'm teaching you the both side of it, not just the practical side, but also the theoretical side, so that you have a well-balanced idea about the concepts that are being taught. And again, I can also say from my own experience, right? After I graduated from master's, I went on to industry to work as software engineer. But then in 2018, I left my job as a software engineer and became a researcher in embedded machine learning, right? And I'm so glad that the concepts like the theory and mathematics behind that topic helped me to like produce some of the influential papers in the area of embedded machine learning and AI. So I also try to do the same even through the lectures so that you have idea of the both the world, like research as well as practicals. Okay, moving on. Excuse me. Let's say now you have a grammar in EBNF form, which can be expressed like this, where you have E produces or derives E plus E, or E star E minus E, E itself, or it can be ID as well, right? So you are given this grammar rule. So for, let's say, if you have the production rule where E produces minus E, the replacement of single E by minus E will be described in this form, E long arrow minus E. So here, this can be then say like expressed or said as E derives minus E. And I've already mentioned this also several times as well. If you have the production E produces like E within bracket, then that can be applied to replace any instance of E in the string of grammar symbol by E within brackets. So what do I mean by that? Let's say if you start with E star E, then here you can replace the E, first E, with E within brackets star E. Or you can also replace the second E here with E within brackets as well. So you can, depending on this grammar, you can replace each of the E based on the other rules that are already part of the grammar itself. So you can also repeatedly apply productions in any order to get a sequence of replacement, as we have already discussed. Now, you have two types of derivations, leftmost derivation and rightmost derivation. In the leftmost derivation, let's say if you have the string minus ID plus ID that within bracket is itself a sentence of the grammar, because so based on this grammar rules, right? If you have E, which is the non-terminal, you replace that with the ID, right? And other rules. So you start from the leftmost side. So as you can see, we start from E, we replace that with minus E, and we then replace the E again with E within bracket. So these are based on the rules we just noticed. And you replace E again with E plus E. And then you replace the left-hand side E with ID, and you replace the right-hand side E with ID. And you can see minus ID plus ID. We have derived this from the left-hand side of the production rule. That's why it's called a leftmost derivation. But if you do the derivation from the right hand side, so here you can see the difference is, instead of replacing the left hand side e, we replace the right hand side e with id first, and then the left hand side e, although the production or the derivation is same as the left hand side for this case, but because the derivation started from the right hand side, we call this the rightmost derivation. Does that make sense so far? Anyone in the chat? Okay, 50-50. Just so Matthew mentioned, just going over it in my head again. Okay, I will explain once more. Okay, this is important because sometimes you might be asked, okay, can you like derive something based on the production rules or grammar, right? So if you are asked to do leftmost derivation, right, you take the start symbol and you replace it with a production rule, which is, let's say in this case, right? So first we are replacing with the production rule minus e, because here in the production rule, we mentioned that e can be minus e, right? So we are replacing the e or deriving, as we call it, deriving to minus e. Then we are replacing the minus e, like the e in the minus e, with e again within brackets. And then we are replacing this e with e plus e, because that's also another production rule, right? Now see, now we have two non-terminals here. If among the two non-terminal, if we start replacing from the left hand side first, which is this e, we can derive id here, right? And then we replace the right hand side and we can derive the next second id here, right? Since we are starting from the leftmost side to replace something based on the rule, that is leftmost derivation. But if instead of replacing the left hand side, which is in this case, we replace the right hand side first to id, then this is called rightmost derivation, because we are starting to replace from the right hand side. Okay, does that make sense now? Okay, Matthew has mentioned leftmost derivation is the same as looking as a tree and working through the branches from left to right, while rightmost is doing the same but from right to left. Yes, it's doing like it's replacing based on the production rule from right to left for rightmost derivation, but for left it does from left to right. Now I will show you another example that the tree, although see, you might have the final output for leftmost derivation as minus id plus id and rightmost derivation minus id plus id, which is same. But because they are derived in different ways, sometimes the tree, the parse tree also might look different. And I will show you with example as well. Because the way you start it, like the replacement or the derivation, also determines how the parse tree will finally look like. Okay, could you, Soren has asked, could you explain the minus derivation again? Soren, just to confirm, you mentioned, you asked that why is this minus sign here? Is that the case? Okay, so the reason why we ask this, let's say if I am asked that you have this grammar, right? So grammar, remember, grammar is a set of production rules. Each production rule for this grammar is, one production rule is E derives E plus E, right? That's one production rule. Another production rule is E derives E star E. That's another production rule, right? Same way, one of the production rule in this grammar is that E can also derive minus E, right? Now, keep these production rule in mind. The reason is because if we are given these production rules or the grammar, and we are asked, okay, can you derive to this? Like, can you derive the input, like the string as minus ID plus ID, right? So if we have to derive this from E, the way we can achieve that, if we go for leftmost derivation, is depending on the production rule. First, we derive the minus E, because we have to get the minus in the string in ID plus ID, right? So we use the production rule that leads to minus E. Then we replace the E with E within bracket. And then using the another production rule. So as you can see, right, you have E within bracket, one of the production rule, another production rule that if you have E, you can also derive E plus E from there as well. So we are replacing or deriving based on that. And we continue till we finally achieve the string, which is minus ID plus ID. Does that make sense now? Sorry. So Matthew has mentioned, so it's just part of the grammar we are using in this example. Yes, this is just an example that if we are asked that based on the grammar or the production rules of E that we just noticed, if you can derive to minus ID plus ID. So your job is, okay, which symbol you can replace depending on the production rule to finally achieve this minus ID plus ID. Okay, cool. So parse tree is technically a graphical representation of a derivation that filter out the order in which productions are applied to replace the non-terminals, which is E in the example that we have just noticed. Each interior node of a parse tree represents the application of a production rule. The interior node is labeled with the non-terminal A in the head of the production. The children of the node are labeled from left to right by the symbols in the body of the production by which this A was replaced during the derivation. Now here A is the non-terminal, keep that in mind, right? The leaves of the parse tree are labeled by non-terminals or terminals and reads from left to right. So here, using, remember the production rules or the grammar of E that we have noticed, right? So we just replace the E with the minus E, we replace E with E within bracket and so on, and we derived minus ID plus ID, right, within brackets. If we follow this form of derivation, then the parse tree will also be something that looks similar to this. We are doing this same exact thing. You have E, you replace the E with minus E, right? So you have minus and E as the children of E. And then you replace the E with the E within bracket. And you carry on expanding it to finally achieve the parse tree that you desire. So, as I have already mentioned earlier, that whether you start from left most derivation or rightmost derivation, although your derivation, final derivation might look the same, but how you derive the parse tree might be different. So for example, again, depending on the grammar or the production rules of E, which is defined here, it will produce two leftmost derivation for the sentence. If you have the string or the sentence like this, you can derive in two ways. And depending on how you derived, the parse tree, as you can see, will also look different, right? So here, the parse tree on the left reflects the commonly assumed precedence of plus and multiplication or star, while the tree on the right-hand side does not. So when you generate the parse tree based on the production rule, right, it's important to provide or add precedence to force the parser to recognize high precedence sub-expressions first. So that's how you can resolve any form of ambiguity. So keep this in mind. Especially this is important in theoretical sense. In practical, ANTLR already does that on its own in the background. But in theory, you should be able to understand this, that ambiguity in grammar to derive parse tree can happen, but the way you resolve it is by adding precedence. Okay, someone mentioned something in the chat. Curtis has asked, can that be done by the order in which you write your rules? Yes. So in practical sense, actually, you will notice that I have already mentioned, when you write the production rules, right, you have to make sure that your precedence is like higher precedence one, production rule goes on top, right? That's one of the way you can define it. So the ANTLR, when it generates the parse tree, it automatically knows from your production rules that which one has higher precedence from the other. So in practical sense, yes, you can, actually you should define the precedence so that ANTLR knows exactly which one is more important production rule than the other, and how the input string should be parsed. Now, there are many different forms of parsing algorithms. They also can be characterized in different ways as well. So one dimension of classification is the direction in which the rules are applied. One example is the top-down rule-driven, which is it uses the rules to expand from left to right, which is this case here, right? So it expands from left to right, and because an expansion is happening, that's an example of the top-down rule-driven approach. The other one could be bottom-down data-driven approach, where let's say if you are given a tree, so you start to compress. So you, instead of expanding, you replace the symbols to compress it, but that happens from right to left. So that approach is called the bottom-up data-driven approach, okay? In the case of context-free grammar, the derivation can be recorded structurally as a tree. That's why we have the output as parse tree. And you should know how to apply the rules manually, as I've already mentioned. So you should be comfortable like expanding. So given the rules like this, you should be comfortable expanding the expanding the non-terminal based on the rules that are provided in the grammar, and all should be able to form the parse tree accordingly as well. Now, another very important topic, right? If you can recall, as I've already mentioned, that in parse tree, when the parsing happens and you generate the parse tree, you can also understand errors happening in this stage as well. A syntax error could occur when the string of input tokens is not a sentence in the language. Let's say in practical sense, I'm very sure like yesterday as well during the lab, I noticed some of you, depending on a grammar that you have defined, sometime when you try to give input string. So one example could be, let's say your grammar that you have defined in your ANTLR is for arithmetic expression, right? But sometime when you try to form the parse tree, you have provided a symbol which doesn't, or expression doesn't fall within your defined arithmetic expression grammar, right? And you will see the parse tree then provides an error. Like you will see EOF and it's marked in red, right? If you have already noticed that, that's also a form of error notification or error observed, because your grammar doesn't include that input string that you're trying to provide. And that's a syntax error because the string of token that is provided to the parser is not part of the sentence or the grammar rule that you have defined for that language. Now, error recovery is itself a way of finding some sentence similar to that string of tokens. This can proceed by deleting, replacing, or inserting tokens. It's a bit dangerous to do error recovery by insertion, because if the error cascades to produce another error, the process then might loop infinitely. So keep that in mind. Error recovery by deletion is actually safer because loop must eventually terminate when end of file is reached. So it's important to understand error, especially because if you can recall, as part of your assignment 1, you also have to do some error handling on your own. So keep this thing in mind because it will help you to program in practical sense as part of your assignment 1. Now, that being said, we have reached the end of today's lecture. We will continue with the second part of grammars and parsing in the next lecture. But let me pause the recording here.